Okay, this is for Sacramento State Physics 5B. This is your own chapter 18. Um, Basically, this is the new PowerPoint. I can't upload it right now because I forgot and started uploading a video for my astronomy class at Sac City, and see, it's going to take 2 hours and 20 minutes, and everything is slow. See, right now, okay, I've got into the file there, but so this PowerPoint that you're looking at right now, this is an updated version from the one that you had. Okay, so anyway, this is your own chapter 18, and we're going to go through the different sections: 18.1, 18.2, 18.3, 18.4, 18.5, and 18.7. So we start off talking about static electricity. Okay, now things rub together. When they rub together, one takes electrons away from the other one, and as a result, one becomes positively charged and negatively charged. Now, wool and cotton, for example, when they rub together, hold on a second. Okay, so I gave you this. Basically, the way this works, these are less tightly bound electrons. So in other words, these guys up here don't hang on to their electrons as much as ones below them on the list. Polyester plastic fabric will give up electrons to everything on the list. And on the other hand, the Teflon will take electrons from everything on the list. So what you do is you look at where two items are on the list. The one higher on the list gives up the electrons to the one lower on the list. Right here we can see there's wool, there's cotton. That means we rub wool and cotton together like in the dryer. Wool will give up electrons to the cotton. Cotton will gain electrons from the wool. The cotton becomes negatively charged. The wool becomes positively charged. And that's what we're trying to show right here. Cotton, wool, they tumble together in the dryer, and they come out where the cotton has gained electrons. It's now negatively charged. They were neutral. And the cotton and the wool has lost electrons. It is now positively charged. And then you're going to get static cling. They're going to try to stick together. Okay, now what is happening at the atomic level? Okay, so basically atoms are made up of electrons, protons, and neutrons. Okay, we're not so much interested in the neutrons at this point. Electrons orbit outside the nucleus. This would be a stable carbon atom. The protons and the neutrons, they are locked inside the nucleus. When we rub two things together, we don't bother with them. But it's the electrons outside the nucleus that we can move around. So if something becomes positive, that's not because it lost protons. Or if it became negative, that's not because, I said it the opposite way. We say something becomes positive, it became positive because it lost electrons, not because it gained protons. And vice versa. If something becomes negative, it became negative because it gained electrons, not because it lost protons. The whole point is it's the electrons we move around, not the protons. Atoms are made up of electrons, protons, and neutrons. Electrons have a negative charge. Protons have a positive charge. Neutrons are neutral. Protons and neutrons reside in the nucleus. They're in there. Electrons orbit the nucleus. So this is the build an atom thing. You can the way you would get to that is you'd simply hold on a second. We're not going to be able to run this while I'm uploading that other video because it's going to take too long. I'll try to remember to go back and do it later. I got like 2 hours on that other video. So anyway, you've got the link right there. This will probably be your first lab, as a matter of fact. I'm working on your first lab. I'm trying to get it to you either tomorrow or Thursday. But this will be your first lab, probably messing around with this and answering questions about building an atom. Okay, so this is basically how atoms are put together. We've also got this one. This is also a PHET. This will probably also be another one of your labs. Or I may combine all three of these into one lab. I don't know. I got to stretch things out. So what is happening at the atomic level? Electrons exist outside the nucleus and can be ripped away from the atom through friction. They then leave that atom as a positive ion. The electrons can then attach to another material and make it more negative. So if you go and you take on PHET, you can't do it right now because, like I said, I'm uploading a video and it's slowing down my. I have very little internet connection right now. Well, that dominates all the bandwidth. So you take the balloon and you rub it up there, and the balloon takes the electrons away from the sweater. Rubber balloon, sweater. So sweater, we could say, is probably wool. Rubber balloon's down here, so the rubber balloon will gain electrons the wool sweater will lose electrons. So you see up here, they're both neutral, so you got pluses and minuses are equal, and if we counted them out, we can see the plus. Actually, you can see every plus has a minus going with it. But now, look at that. Some of these pluses are missing negative electrons because they've gone onto the balloon, and now these two will stick together. So these are the symbols we're going to use. E, little e with a minus sign is going to be an electron. A p with a plus is going to be a proton. An n with a little zero, that's going to be a neutron. Charge is measured in units of coulombs. An electron has a charge of minus 1.6 times 10 to the minus 19 coulombs. Proton has a charge of plus 1.6 times 10 to the minus 19 coulombs. Neutrons are neutral, thus the name, and do not take part in electrostatics. They're not important. They're locked away in the nucleus anyway. They don't contribute to the plus and minus part of this. And you've got all of this here. See, there you got the charge of the electron, charge of the proton, mass of this is on canvas. This is on canvas. Okay, conservation of charge. Charge can either not be created nor destroyed. The total amount of charge in the universe is a conserved quantity. Okay, so if you're going to have a negative charge disappear, you got to have a positive charge disappear at the same time. So you have run into the law of conserved quantities at this point. You've learned about conservation of energy, momentum, angular momentum, and so on. Electric charge is also a conserved quantity. The number of electrons entering the node, this was something we'll run into later. Electrons come in, electrons go out. You got 100 million electrons going in. These two better total 100 million electrons, okay? The amount of charge going in has to equal the amount of charge going out. Here you even got special cases the book talks about where energy can be turned into matter. That's Einstein's famous E equals mc squared equation. Energy can be turned into matter. So here it's being turned into an electron and an anti-electron, sometimes called a positron, I believe. But one's positive, one's negative. So you did not change the net charge of the universe. Okay. Also, this was what happens in the center of the sun. An anti-electron is created, and the anti-electron and an electron come together. They annihilate each other. They send off energy in the form of a gamma ray. So Einstein gave us the fact that we can convert back and forth between energy and matter. Even in this case, charge must be conserved. Energy converted into electron and anti-electron, so net charge in the universe remains unchanged. Electron and anti-electron can annihilate each other to generate energy, and still the net charge in the universe remains the same. Okay, you don't have any more electrons compared to protons. and the energy going off here would be a gamma ray. Okay, this is John for voltage. This is another one that we'll probably run. I can't run it now because I'm uploading that other video. I've got to time uploading videos differently now. Okay, John for voltage scuffed his foot on the rug and transferred 7 times 10 to the 15 electrons to his body, and then discharged into the door. How much charge passed through his body? Okay, so Q, the amount of charge that passed through his body, that's the number of electrons times the charge per electron. So you get 7 times 10 to the 15th electrons total. Each electron is, I dropped the minus sign here, but it should be probably minus. 1.6 times 10 to the minus 19 coulombs, so for a total of 1.12 times 10 to the minus 3 coulombs of charge would have passed through John Travoltage's body. And then this is a nice video showing you simple experiments you can conduct at home. And again, I can't show it here because that'll take up bandwidth and make this video take forever to upload. But there it is. You've got the link to it. You can watch it. And it's pretty amazing some of the things they can do with just simple PVC pipe, aluminum can, and so on. And you can really, be like a magician and get people all excited. Here's the balloon electricity. This is where it is. This is the one I had pictures of up here. See, there's the pictures. I got them from there. So balloon, sweater, rub the balloon on the sweater. Okay, so there's the link. Again, we can't do it now because of this going on. This is taking up, it's going to take another 2 hours and 12 minutes. Maybe I'll come back and complete this video then and do them. I'm not sure. Or maybe I'll do them on a future video when I'm not uploading something. Okay. Now, conductors and insulators. This is chapter 18.2. Chapter 18, section 2. Metals and water with ions, salt water for example, make good conductors. Okay. There are a number of free electrons that are able to carry current, or free ions in the case of the water, able to carry current and heat easily. Especially the current is which we're kind of interested in. So, free electrons, because not all the electrons are required for metals to make their bonds. Some of them just become like orphans, just like out there by themselves. They're not really attached to a nucleus at all. So they can carry current and heat from one place to another very easily. Copper wire is a very good conductor, and also copper isn't that expensive, and it's a better conductor. I believe it's a better conductor than gold. Gold is also a very good conductor. So we're fortunate we've got copper. It's very, very good conductor, and it's not that expensive compared to gold and silver, for example. Now, insulators. Most materials are insulators. You think of metals, and you think of water with impurities in it, then everything else you think of is probably going to be an insulator, like wood, for example. Electrons are held in they're all needed. All the electrons are needed to create the structure of the material. All right, insulators are poor conductors of current and heat. It should be of. Oops, you got an or on yours already. Oh, I haven't uploaded this yet because I haven't uploaded this yet because I forgot to upload it before I went ahead and started uploading the video for the astronomy. Okay, wood, rubber, glass are just a few of the many examples of insulators. Okay, so these would be insulators. Coulomb's law. Okay, I think before we do Coulomb's law, we can do the. Okay, so this is your worksheet. No. This is your worksheet. Okay. I'm not going to add any more problems. That's your homework, and the quiz we take on Thursday will be based on these few little problems here. Okay, I'm saying this on a Tuesday, so when you're watching this, it's probably tomorrow. But anyway, you already have the problems. You already have the reading. Sections 1, 2, 3. So these are what Coulomb's law is coming up. But okay, first of all, water starts off its existence as a polarized molecule. A stream of water is deflected towards a nearby electrical charge that is brought closer to it. The sign of the charge of the object is positive, negative, or zero, or can't be determined by the information given. Think about it. So you've got your water molecule. One side is positive. That's the side the hydrogens are on. Hold on, I think I did this. Okay, I did make a picture. Just so you're not confused, I'm back over here. Okay, you didn't see this before because I just added it just now. But here's the question. Water starts off its existence as a polarized molecule. A stream of water is deflected towards a nearby electrically charged object. That would be this guy right here. That is brought closer to it. The sign of the charge of the object is positive, negative, zero, can't be determined by the information given. This is water just flowing down. Okay, you got the Mickey Mouse head. This is the oxygen. These are the two hydrogens. The oxygen side pulls electrons towards it because it's got more protons in its nucleus. It's got like 8 protons in its nucleus. Hydrogen only has 1. So the electrons are attracted this way. So this side becomes more negative, leaving this side more positive. That's what I mean by it's polarized. And they're just randomly falling in all sorts of orientations. When you bring some negatively charged object close to it, the water molecule is going to flip. It'll flip such that the more positive side is closer, not only closer, but then attracted to the negative PVC pipe. Okay, so you might say, well, that means that it must be negative. Well, this took me a long time to do, and I got tired of doing it. So, but just imagine what's going to happen if you bring a positive object here. All the water molecules will flip the other way, so that the negative, if this is positive, they'll flip so the negative side is closer. They'll be the Mickey Mouse ears will be on this side, so that the negative side is closer to the positive, and they'll do the same thing. So the answer actually is can't be determined by the information given. We don't know if it's a positive or a negative. You hold the PVC pipe or whatever up close to the water, the balloon or whatever, and the water is deflected towards it. Okay, we don't know whether the object is positive or negative because the water would react the same either way. It would just flip different ways. We can see which way the water flipped, but we can't. Okay, that's an experiment you can try with the water flowing and take something and charge it. You see how to do the charging in these videos. That's right, they're down here now. All right, so that takes care of this guy. Okay. Now this one here, this is number 2 in your own. You have number 1. You have number 1. This is number 2. Where's number 2? Okay. If 1.8 times 10 to the 20 electrons move through a pocket calculator during a full day's operation, how many coulombs of charge move through it? Okay, this is actually pretty easy because you didn't have to take, you already know how many electrons move through there. So that many electrons, you know what the charge is on each electron. So there's that many electrons, that's the charge for each electron. Q is going to be equal to the number of electrons times the charge of each electron. So it's going to be minus 28.8 coulombs of charge would have moved through that pocket calculator in a full day's operation. Okay, then this is number 4. You have number 3. You've got 3. This is number 4. Okay, so number 4 on your own. It's number 3. See, this is 1, 2, 3. So it's 3 on the worksheet, but number 4 in chapter 18 in your own. A certain lightning bolt moves 40 coulombs of charge. How many fundamental units of charge QE is this? Okay, so again, we want to find out the number. We've got the amount of charge. It's opposite of this one. We've got the total amount of charge. We want to know how many electrons or protons, whatever, 1.6 times 10 to the minus 19. How many of these do we have? Absolute values. We're just looking for a number. Okay. So again, the amount of charge is going to equal to the number we have passed by times each one's charge. So N equals Q over QE. That'd be the 40 coulombs of charge divided by the charge of each individual particle, and we get 2.50 times 10 to the 20 particles. Electrons, probably protons, probably electrons in this case. Okay. Okay, now there's Coulomb's law. So let's go back to the. We're down here someplace. Okay, Coulomb's law. Okay, it looks a lot like Newton's universal law of gravitation. The differences are basically the instead of the universal gravitational constant, we've got the K here. That's Coulomb's constant. Instead of mass 1 times mass 2, we've got charge 1 times charge 2. But still the distance between them squared. Okay, just like Newton's universal law of gravitation, which you might have studied in 5A. So K is Coulomb's constant. There it is right there. It's easy to remember. 9.00 times 10 to the 9th newtons meters squared per coulomb squared. We know we want to get newtons because we got force out here. We got to get rid of the meters. So we put the meters on top squared because we got distance on bottom squared in meters. We put the coulomb squared on the bottom because we got the Q1, Q2 on top here. Q1 and Q2 are the charges and have units of coulombs. R is the distance between the charges and are in units of meters. Okay, so this is out of your book. So you can see that if they're the same, like two negative charges, they would repel each other, or if they're opposite charges, they would attract each other. So now we want to talk about what is an electric field. Actually, now we can go do Coulomb's law. So, how strong is the attractive force between a glass rod and with a 0.700 microcoulomb charge and a silk cloth with a minus 0.600 microcoulomb charge, which are 12 centimeters apart? Using the approximation, they act like point charges. Okay, so we use Coulomb's law. We know what K. Well, I got 8.99 here instead of 9. Okay, but we take charge 1. Okay, that would be the 7.00 microcoulombs times 10 to the minus 6 coulombs, times the charge 2, that's the minus 6.00 microcoulombs, or minus 0.600 times 10 to the minus 6 coulombs. Okay, and then divided by the distance between them squared. Well, 12 centimeters is 0.120 meters. Okay, this book likes 3 significant digits. Notice all those numbers have 3 significant digits, and the answer is in 3 significant digits. We probably want to stick to try to do things in 3 significant digits when we can. All right, so we just multiply it out. We get minus 0.2662622 newtons, but we just want the absolute value. So the force is going to be 0.262 newtons between these two objects. And here we have, is that it? If two equal charges of 1 coulomb each are separated in air by a distance of 1 kilometer, what is the magnitude of the force between them? You will see that even at a distance as large as 1 kilogram, the repulsive force is substantial because 1 coulomb is a very significant amount of charge. Okay, so wait. Oh, because they're both 1 coulomb. Okay, that number there is K. That's the K. We're back to 9.0. I got confused there for a second. All right, so K, 9.0 times 10 to the 9th newtons meters squared per coulomb squared. And then you've got 1 coulomb and 1 coulomb. So you got 1 coulomb squared, and then you're dividing by your 1 kilogram, 1 kilometer, which is 1 times 10 to the 3 meters. So 9 times 10 to the 3 newtons would be the charge between those, because 1 coulomb is huge. Remember, each individual electron is 1.6 times 10 to the minus 19 coulombs. So 1 coulomb is a huge, huge number, and that's it for the problems. So that kind of covers whatever I'm going to ask you on the quiz on Thursday. Okay, and then we got this other stuff about, well, plus you want to try to understand electric fields and so on. So in science, what do we mean by a field? A field is a space in which we can measure some quantity at a number of different locations. So here I found this temperature field on the internet someplace. So the red is the hotter, see this is in Celsius if you can read that. The red is the hotter, that's 20, 30, 25, 35, and it goes down all the way to the violet blue being the cooler, okay? You can see along the equator, which gets more sun than the rest of the surface of the earth on average, it's going to be warmer there. We'll be up here in Sacramento, we're in the green area, so that's about 20, so that's about right, 20 some odd degrees Celsius. So it really does get warm down there at the equator, doesn't it? Wow. Okay, then up here, now you're getting into Alaska and places like that. That's because it's going to be cold up there. So you can go around with a thermometer and measure all these and make a temperature field. So you got data showing you, and you got position, you got data. Data, position. Okay, now you got yourself a field. Okay, now what about a gravitational force field? So you're already familiar with gravity from Physics 5A, or yeah, Physics 5A. So you've got the Earth, okay? Now we want to go around and put satellites. These are like satellites. They're supposed to be satellites, okay? Again, it's an amateur picture. I made it myself because I couldn't really find anything on the internet I liked. So, and this is why this is taking me so long to do this stuff. I'm not that fast doing this. But you've got the Earth. See, I'd normally be drawing this on a board. So you got the Earth. You've got the satellite that's pretty close, so we know it's going to have a larger gravitational field. Remember, here you got, this is Newton's universal law of gravitation. Instead of Q1, Q2, we just saw it's M1, M2, still divided by the distance between them squared, and then you got the universal gravitational constant. So now you've got this guy right here. It's got that much force on him. That guy here is pretty close. They got that much force on him. You go further away, they got not so much force on him. So we go here, put the satellite there, and we can measure the force on that satellite. So we can go around, put our satellite all over the place, way out here, over here, everywhere, and we can measure what the forces are. We can map out a gravitational field showing what the forces are, and also they've got direction. Unlike the temperature field, this doesn't have the direction associated with it, right? Temperature does. Temperature gradient, maybe. How does the temperature change? Okay, but temperature itself does not. But the gravitational force does, pointing in towards the Earth. It does have a direction associated with it. So this is a field that has a direction and a magnitude associated with it. Okay, so unlike temperature field, the gravitational field also has direction associated with it. Now, what about an electric field? So now instead of the Earth, we got a proton there. It's like a proton in there. And so anything that's has a charge is going to feel a force due to that proton. So instead of satellites, I've got electrons in here. Okay, so if your electrons are close, we can take electron and put it here, our test charge. We're going to call it test charge, test charge. Put our test charge all over. We can see what is the force going to be due to this electric force field. And in here, your electrons are kind of close. They're going to have large forces acting on them. Here, your electrons are further away. They're going to have smaller forces acting on them. You can imagine going around all over the place on this thing. I think there's even there's a PHET we can look at. But we've already got 3 PHETs I want to look at. So we'll save that one for later. Okay, so again, there's Coulomb's law. Look how close it is to Newton's law. There's Newton. There's Coulomb. Oops, why am I there? Oh, that should not be a G there. Okay, you guys have not. That should be, I believe, I'm going to put a C there for Coulomb. Okay, I haven't uploaded this yet, so you'll see the corrected version. Okay, so we got the K, we got Q, and everything else is right. I just added G there instead of a FC, so they can see how those two are so similar to each other. Okay, closer charges experience a greater force. Objects further away experience a smaller force. So we can go around and map out a force field. Okay, so this is from I took this from your book, electric field. To measure the electric field strength at any point, we stick a test charge at that point and measure the force on that charge. But we want a definition of the electric field that is independent of the test charge. In other words, you put something there, that object is responsible for the electric field. Or you put a bunch of objects someplace and you got a certain electric field. What we want to say is, okay, if you put a test charge here, okay, that's the electric field it's going to experience, and so it's going to have so much force acting on it. So the way we do that is that we take Q as the charge generating the electric field. So there's Q. The electric field around Q exists because of Q, okay? Everything we put in there is going to feel force because of Q. We put a test charge in there, okay? So, and then they made it plus because normally we think of electric fields as going out away from protons or plus charges. All right, so you've got your force, and then Q is the charge generating the field. Q1 and Q2 are like the test charges. Take E to be the electric field strength, okay? So E is force divided by the charge of the test charge. So in other words, E is going to be in newtons per coulomb. It tells you that if you put this many coulombs there, it's going to feel this much force. And you can see it's a ratio. So at any point around there, we can have an electric field that's in newtons per coulomb, where F is the force that would be experienced by some random test charge, Q. So you've got that. So here we've got it in the it's here. There's coulombs. There we have it. So you've got the E, you've got the force on the test charge divided by the test charge. So force then equals the charge you stuck in there times the electric field. So if the charge is 2 coulombs and the electric field is 4 newtons per coulomb, then you'd have 4 divided by 2. You'd have 8 newtons of force for that 2 coulomb charge you stuck in there. Okay? Okay. Now we draw the field lines going off away from a positive charge. If this was a negative charge we had here, this was a negative charge, we would have the field lines coming in towards it. Electric field is force per charge, okay? In other words, it tells us that if we stick a random charge into this field, that this is the force it would experience. So you stick some bunch of coulombs there, and at that point in that field, this is the force that they would feel, okay? E has units of newtons per coulomb. It has newtons per coulomb now, but it's also, we're going to see it in, it's always going to be newtons per coulomb, but we'll see that newtons per coulomb is going to be the same as volts per meter. So later you'll see it as volts per meter. F equals Q over E. You have an electric field with a strength of 10 newtons per coulomb at some point. This is completely independent of the test charge. You place 2 coulombs charge at this point. What force does it experience? Well, you got 2 coulombs. For every 1 coulomb, it's going to experience 10 newtons of force. So 2 coulombs would experience 20 newtons of force. Okay, not too complicated at all. These are the homework problems that'll be next. Okay, I'll start lining those up. I haven't gone through them yet. Well, I have, but that was last semester. So and I haven't gotten around to, I've got so much stuff to do, I haven't gotten around to that. I think we're done. Okay, so this is everything here. We did all the questions on our in thing, so you should be able to hand that in. This is it. Okay, so you don't have this filled in. In other words, you don't have these. I want you to try. You've got the answers here, so you might want to try them without looking at this, and you can go back and look at this and see what you did. Okay, you've got the questions that'll be due on the, see, today is the 7th, so they'll be due the 9th. Okay, and then you've got the answers down here. so you can work towards the answers. And then also we'll have the quiz we'll have on Thursday will just be over this. So it'll be a very simple quiz to start the semester with. Okay, I think that's everything. The longer I go, the longer it's going to take me to upload this. And the other video is not even close to an hour and 51 minutes. And I can't do anything while this is doing that. See, if we got the, see look, PHET, it's not even loading these guys. It's not even loading the pictures. This is as far as it's got. There's the balloon and buoyant, no, that's balloon and buoyancy. Balloons and static, that's the one I showed you. I'm also, the build an atom is here. It's not, the pictures aren't loading because it's taking too long. And then down here is John for voltage. Just, is there an alphabetical order? John for, past them. I think it's John, G-H-I-J, John for voltage. There it is right there. So those are the ones that you can mess around with. And they're probably going to be the lab that I'm going to give you hopefully on Thursday, okay? Alright, so I think that's everything. I don't know how long this has taken, but if it's an hour long, it's going to take 8 hours to upload. So I'll send out a blast email. I guess you students have been calling it a blast email, and then tell you that this is available, and it's a brand new a brand new PowerPoint presentation. So let me hit pause now and call it a night, or not a night, but I still got to upload this. Alright, so talk to you later. Good night, good afternoon, whenever you're watching this.